Good morning, sir. My name is Timothy Thomas George, 20 BCE 1278, and I will be presenting the topic transaction structures. Before I go to the presentation, I want to show the code implementation of what I will be describing. So then we can see the presentation after that. So this is the Remix IDE where we can execute Solidity programs, we can execute smart contracts and scripts and compile them and run it within Remix. Remix is an online IDE for doing Ethereum programming in Solidity. Here in our first program, we have something called, yes, UTXO. These are unspent transactions. And the idea behind this is everybody who has bitcoins or blockchain coins that are unspent, these are saved in a pool. And from that pool, we need to find how many coins point to one particular address. So in this program, we can see first there's the importing and all that is happening, and we are giving an address. So this address is basically the public key of one user. We want to search in the pool for all coins that point to this address. So we put we declare a variable resp and put request.getOf, and then we connect to blockchain.info. This we are assuming as the API URL, the application programming interface, where it will contain the pool of all the transactions. And then we put unspent active is equal to the variable address. This address is what we had defined in the beginning, const address, and we gave this address. So what this function will do, it will get those transactions, those unspent transactions from the pool, from that API, which point to this address. So effectively what this means is these are the coins that are owned by that address. So although this seems like we're just finding unspent transactions, this is actually finding what is the amount of money in the wallet of this person whose address is given here. And then what we do, we load the JSON from that response.txt where unspent outputs is for the value of this unspent outputs key. So what will this JSON object? What is it? So here we have the structure of what the JSON object will look like. There are 7 fields in unspent outputs. The first one is TX hash, which is basically the transaction hash. That means when two people, let's say Alice is paying Bob maybe 5 coins, and 5 coins are going back to Alice. 5 coins to Alice itself is an unspent transaction, which is coming back to Alice's account. The hash of that transaction is transaction hash. Transaction index, TX index, that is this number that counts in the blockchain what number transaction it is. And transaction output number 1. That means we know that transaction can have many inputs, many outputs, can go to one person to many people. But when it's a unspent transaction, the output has to go to one person, because when Alice is paying Bob and Alice pays Bob 5 coins and 5 coins come back to her, the 5 coins coming back to her, the output is only one person. It's back to Alice. So that's why the number of transactions here is 1. Then the script. This is not exactly the script, it's actually the hash value of this script, of this whole script that we can, that the script for a transaction would be locking and unlocking. A locking script is what sets the transaction for a particular person, and the unlocking script is done by the receiver who needs to redeem the transaction. Then we see value. Value is how many coins are unspent, or what, not coins, whatever unit, or how many units of those coins are unspent. Now you have to remember in Bitcoin, in the unspent transactions always in Satoshi unit. So here we have uh, 8 million Satoshis. Yes, 8 million Satoshis. This is the value that is unspent and has to go back to the first address we had seen, Dorian. Uh, Value in hex, the value in hexadecimal representation, and then we can see confirmations. What is confirmations? Confirmations means when we put a block into a blockchain, and when other nodes accept that that block is valid, it will add its own block, and that's how the blockchain extends. We have the first block, then after that more blocks come, and the blockchain gets long. So how many number of blocks come after that? Those are that many confirmations, because each block is coming from one particular node. So when we say 28,691 confirmations, that means after that after that block which had that transaction, Phi to Alice, that transaction, after that block, 28,000 more blocks have come, which means that many confirmations, that many nodes have put that block after that in the blockchain. This is the structure of the JSON thing, JSON object. Then finally, we have our printing statement for uh, constant in the unspent transaction set. We are printing everything console.log of. We are printing the transaction hash value, that is this thing, the hash of the transaction, and number of outputs, that here is 1, and how many satoshis value, so that here is 8 billion. So that will print on the when we run this program. But when we try to compile it, there's some errors with the packages. That's why it's not running. But the output we know will be the hash, number of outputs, then it'll say 8,000 satoshis. So that gives us how many we want to find, how many satoshis is unspent by Dorian, and it will give us the list. If you want, we can even say yes, if they are multiple, it'll show all the unspent transactions and all the satoshis that are in that transaction. It'll give, so in total it'll give the total wallet of Dorian, this address, the total wallet of this address. Okay, now let's see the explanation. We'll go to the other code after this. So we saw transaction ID, we saw inputs, we saw outputs, version number, that is what version of the Solidity is running, of the Bitcoin program it's running, log time. Now log time is how long uh, it's a limit to when the this transaction can be redeemed. So if you want to set, let's say, after this particular time, you should not redeem the transaction. So you will set a log time to that particular time. So till that log time is over, let's say it's 100 hours. So for 100 hours, they'll not be able to redeem that transaction. Then after that, they'll be able to redeem and they can go. Or within 100 hours, we need to redeem that transaction. It's like in network, we have timeout. It's similar to that. And transaction outputs and inputs. Output is the value being transferred that we saw. We saw the 8,000 Satoshi, and it must have the public address, the person who it is, the amount of Bitcoin, and the lock risk. And the input, where it came from, that will be the signature of that person who made that transaction, the unlocking script, and it will be reference to that. So that's how we know that that transaction is valid. And it can have multiple inputs and outputs. And transactions must balance. That means 5 is coming back. The total number of 10, that means 10, let's say Alice is paying Bob. Alice is paying 5 bitcoins to Bob, and 5 bitcoins go back to Alice. Alice should have had 10 bitcoins in the beginning. Then only this is possible. And Satoshi. Satoshi is the smallest unit of Bitcoin, and named after, of course, Satoshi Nakamoto. And it is used, such a small value is used because most of the things do not happen in terms of Bitcoin. No, it happens in terms of fraction of Bitcoin. That's why Satoshi value is used. And Satoshi is the smallest. We cannot go below that. That's why we saw in that script 8 million Satoshis. Then UTXO is what we saw, unspent transaction output. And each unspent transaction represents single unspent output from previous Bitcoin's transactions. And that is used as the input to new ones. That means when Alice wants to pay somebody else the next time, it will take how many unspent Satoshis it has in its pool and use that to pay somebody else. Some Carol. It's paid Bob. Now he wants to pay somebody else. It'll take from the Satoshis that are unspent. And when an unspent transaction is spent, new unspent transactions. Again, when that happens to when Alice pays to somebody else, there also maybe, so we have 5 bitcoins left, maybe 3 are paid and 2 come back to Alice. And that 2 will go back to the unspent transaction pool. And these are all stored on the blockchain. So everybody has access to this, everybody can see this. Now is the transaction fees. What is transaction fees? We know transaction fees is for every transaction, there is a certain amount that is taken by the miners and as fees, as gas. This is gas. And this gas fee is for every transaction. And again, this is based on this. So this can also be tracked because of the scripts that are happening in the transaction. And its benefits include incentivizing miners, and it's also measured in, again, Satoshis, which is the smallest. Okay. And transaction chain. Transaction chaining is linking multiple transactions together. Output from one transaction can be used as input. That is again unspent transaction, where we have one transaction, then that transaction is being referenced when Alice wants to pay the third person. And this enables more complex transactions, yes. And each transaction must be confirmed by the miners. That's why we saw in the script. Confirmations, that many. Orphan transactions. Before we go to, okay, orphan transactions. Orphan transactions are transactions that are not included due to a fork. What is a fork? So let's say there's a blockchain, and Alice and Bob, Alice pays Bob, and that transaction comes in the block. That block comes in the blockchain, and Alice tries to do a double spend and pays Carol also the same amount, and then it's linked to the previous transaction. So then we have a fork. There's 2 blocks: Alice paying Bob and Alice paying Carol, and it's the same coin. So that causes a division. So now, depending which block will get confirmed, only one block can get confirmed and form the chain. The other one will be ignored. And so that ignored block becomes the orphan block. This is usually due to this can happen because of double spend. Okay, script construction. Let us see now the other code. Okay. So when somebody wants to pay someone else, we need to find how much of bitcoins need to be sent. For example, Alice has 10 coins. Let me type it here. Uh, Alice has, let's say, 10 bitcoins and wants to pay Bob 5. Now uh, let's say Alice cannot split her 10 Bitcoin. So instead, so what happens is Alice will pay 5. Let's say the minimum is 5. It's unsplittable in, it's not, just take the example, unsplit. You cannot split 5, 5 Bitcoins. This is not true. We can go all the way till Satoshi value, almost 10 raised to minus 8. But Alice will pay 5 to Bob, and Bob and 5 Bitcoin will come back to Alice. So we need to find how much should be paid to Bob. We cannot pay like three three plus 3 Bitcoins, because 5 is unsuitable in this case. So the problem here is, how can we find what is the value? Like for example, if Alice were to pay 6, then Bob would have to pay. There would be something called change. Change here would be 1. Why? Because Alice is paying 1 extra to Bob. If this is like, for example, if 6 was, instead of 5 it is 6, and 6 is unsplittable, and Alice will pay Bob 6, then change will be a value which is called change, which Bob needs to pay back. This is 1. So how can you find this in terms of unspent transactions? Because we know unspent transactions are all in one pool. Now we need to take from that pool how much can be split and how much you can pay to Bob. Problem with this is, it should either be greater than the value. Let's say if Bob was asking for 5, you can either pay like 6, 7, or you can pay exact 5. So it's equal to or greater than. How can we find this? That is what this code is going to show. So again, we're doing some importing, and it's a greedy approach. Greedy approach is being used. We're going to define a function for greedy approach, and we're going to. So we'll start with the main function. They have defined output as these all. We'll see the class definition later, but what this basically is, they are giving hash, number of outputs, Satoshi values. So in the first, we can see 8 million Satoshis. And this next one, we can see uh, 16 million Satoshis. So in total, this belongs to some person. And we cannot split this because this is one transaction. How do we choose the least number of transactions that is greater than or equal to how much needs to be paid? That is the problem statement. And so we have, let's say we have here given the target, to define the target as, we want the value to be this much. This is 55 million. 55 million Satoshis need to be paid. How will we pay it? That is the question. And so we do all these unspent transactions, we put into select output greedy. We're going to use greedy approach. Unspent transactions are all these transactions you have seen, and the target is how much? 55 million. Now let us see the class definition. The function, yes. So the class definition says, again, transaction has index and number of Satoshis. This is a constructor. This same like how we see in OOPS. Assigning the transaction has, assigning the index, assigning the values. Now to the you have defined toString, it will basically convert. It will give the transaction has index and how many Satoshis. This is just for printing. Now let us see the greedy approach. The greedy approach uses so how the greedy, we will see how the greedy approach through the code. So first is the edge case 0. If nothing is required, if nothing is spent, so nothing can be taken, return null null. This what we're returning is how many how what is the order of such blockchain transactions that we are given. So if there's nothing, it is unspent, then we cannot spend anything, so null. So that's the edge case. Okay. So we define lessers and greaters. We split the transactions, the unspent transactions. We have all the transactions, we split, filter the transactions which value is less than the minimum value. And the greaters, split the unspent transactions where the value is greater than the minimum value. Minimum value is the number that the target that we have given. So now we have split the transaction. Next is if greaters or length is greater than 0. That means if we have any greaters, any transactions that are greater than the target. What is given is mean greater, which we're defining, is greater as a reduce of previous current, where previous value is lesser than current value. If previous value is lesser than current value, take the previous, else take the current. What does that mean? What we are trying to do is we're trying to find the if previous value is lesser than current value. Yeah. So what we're trying to find is what is the least value which we can take in that set. What is the least, like we have, let's say we have 5, 10, 15, 20, and our target is 3. So which one will we want to take? 5, 10, 15, or 20? Which one will we pay? We'll want to pay 5. So that will generate the least amount of change. So that's what this code will do. It will check what is the minimum among set graders. Then it will define what is change. Min greater dot value minus the minimum value. So here the change will be, in that step the change will be 5 minus 3, 2. And then it will return here, and in this case it will return minimum greater 5 change 3 for when the target was 2. Okay. Now let's say this is if the case if they work transaction that is greater than the target. Now let's suppose there is no. So then this code will execute. Now what we in now it takes which ones are lesser. So let's say in this case we have again target is, let's say, 10, and the transactions are, let's say, so 2, 4, 6. Okay. What it's going to do is it's going to sort. First we sort them all. 2, 4, 6. It will come like this. Sorted. Now, so now what we're going to do is we're going to start iterating through this function, and we are going to keep adding in accumulate. So let's work out this function. Let's work it here. So first it will take 6. It will add it to the accumulate. So first accumulate is 0. Then when 6 get added, first 6 will go, it will go 6. Will get added. If accumulate is greater than minimum value, is it greater? No, minimum value is target, which is 10. No, again this will repeat. Then we'll take the next one, 4. It will push into the result and it will add to the accumulate. So next will be 6. 6 plus 4, it will be 10. Then what happens? If accumulate is greater than minimum value, is it greater than minimum value, greater than equal to? It is greater than equal. That's it. Here we stop. So what is the then what is the result? Result has what? Result has it has 6 and it has 10. 6 and it has 4. Then what we do, constant change is equal to accumulate minus minimum value. So accumulate last was 10 minus minimum value, that was 10. So changes 0. Then return result, it'll return what? It will return 6, 4, and it will return change, which is 0. So this is how, this is for target 10. So this is how it will find how much block should be set. If everything should fail, if we're not able to get, then it should result, it should return null. That means no, we cannot find any blocks. That's the last case. Else it will either catch it here or it will catch it here. And that result will come back to this and it will be printed. Again, because of packet issues, I cannot run this code, but this is how it is coded. This is how it is done in TypeScript. Okay, let us come back to PPT. We have seen often transactions. Okay. Script construction. How do we, so now we know how to find the unspent transactions and how to find how many to pay. So more about the scripts. These scripts are constructed as for locking and unlocking. Once we have found, now we got that result set. That result set needs to be unlocked for the person to realize it. So locking scripts are used to specify conditions when it can be spent, and unlocking provides proof that of the outwards locking script. So when you enter redeem it, then he should have the proper signature because this is signed with his public address. And scripting language. So that language which we saw was TypeScript, and Bitcoin uses a stack-based scripting language. We have seen earlier the operand, pubkey hash, that stack-based scripting language. And this gives us options for a lot of opcodes and stack operations. And scripting language allows for complex conditions to be specified, such as time blocks or multi-party signatures. Multi-party signatures means like the one we saw in escrow transactions. We can have Alice paying Bob, and then one trusted third party, let's say a bank, it is also putting its signature. So Alice will pay Bob with that signature. So two people say Alice and the bank. Alice is paying Bob, bank is a trusted third party. It will also sign that transaction. So transaction will have Alice and bank, multi-part. And that is my presentation on transaction structures with theoretical description of transaction structures and code. Thank you, sir.